Hello, geometry students. So today we're going to be moving on from section 2-2 and into 2-3, and now we're talking about biconditionals and definitions. So we've already talked about if-then statements, but now we're going to take that a step further with something called a biconditional. So what I'd like for you to be able to do by the end of these notes is to write a conditional and a biconditional statement as well as their converses, and then determine if certain biconditionals are true or not. And of course, if they're false, then we'll need to prove that they're false by using a counterexample. So that's the goal for today's set of notes. Let's jump right in with some definitions. First of all, what is a biconditional? A biconditional is a single true statement. That has the following, and we're going to list three other things. Has the following. First of all, it's going to have a conditional and its true converse. Now, yesterday we talked about what a converse is. Remember, a converse is when you have an if-then statement and you switch the hypothesis and conclusion. So it's kind of like the sentence backwards. So a conditional and its backwards true sentence as well. A biconditional only works, or it's only true, when it is true both forwards and backwards. So it's important that it's true both forwards and backwards. Okay, now just like a conditional uses if-then, a biconditional is going to use a specific phrase for it as well. And it is going to use if and only if. So for example, I am happy if and only if I am smiling. That is how we would use that if and only if phrase. And so we're using if and only if in a biconditional instead of if-then. If you don't want to always write out this whole phrase, if and only if, there is a little abbreviation for it, and that is IFF. So I'll just put that in little parentheses down here. IFF means if and only if, just abbreviated. So these are all the conditions that need to be met for something to be a biconditional. Let's kind of see that in action with a couple examples. So first we have example 1, and it says write the conditional statement and converse within the biconditional. So we already have a biconditional. We're going to write it as two individual conditionals, being the converse of each other. So here it says, you live in Washington, D.C. if and only if you live in the capital of the U.S. So we're going to break this up into an if-then statement first. We know it's a biconditional because of the if and only if, but we just want it to be a regular conditional. So the first one is going to be, if you live in Washington, D.C., then you live in the capital of the U.S. So let's go ahead and write that out. If you live in Washington, D.C., then you live in the capital of the U.S. Okay, so this was my first statement. Now I need to make my second statement, and it's going to be the converse. And once again, the converse is this phrase flip-flopped around or backwards. So now it's going to say, if you live in the capital of the U.S., then you live in Washington, D.C. So if you live in the capital of the U.S., then you live in Washington, D.C. So here, this is just kind of showing to you, kind of broken down, how we need both of these statements to be true in order for our if and only if statement to be justified and valid. Okay, in this next example, we have a math phrase, an algebraic phrase actually, and it says for each conditional, write the converse and a biconditional statement. So here we have a conditional. It says if 5x minus 8 is equal to 3x, then x equals 9. So it's an if-then statement. First, I'm going to write the converse. So I'll do that first. Converse, once again, is when you flip these two things backwards. So it's going to say if x equals 9, then 5x minus 8 is equal to 37. So that's the converse. Now I'm going to write the biconditional statement. And remember, biconditional is with the if and only if. So here we're going to say 5x minus 8 is equal to 37. If and only if, and I'll go ahead and put in my symbol. This means if and only if again. X equals 9. So let's read that out loud one more time. 5x minus 8 is equal to 37 if and only if x equals 9. So there we did it. We did the converse and the biconditional, so we're done with that example. Flipping our paper over, we are going to determine if the biconditional is true, and if it's false, then we need to give a counterexample. So it says a rectangle has side lengths of 12 centimeters and 25 centimeters if and only if its area is 300 centimeters squared. So sometimes the if and only if can make stuff a little challenging for us to wrap our heads around. So one strategy you can do is break this up into its two conditionals being the converse of each other. So let's go ahead and do that and see if the two conditionals are true, and that will help us out. So let's go ahead and write the first one, and it's going to be if a rectangle has side lengths of 12 centimeters and 25 centimeters, then its area is 300 centimeters squared. So if a rectangle has side lengths of 12 centimeters and 25 centimeters, then its area is 300 centimeters squared. Okay, and then we ask ourselves, is that true? And yes, it is. So I'll just put a little check mark kind of denoting, yes, that's true. The next one that we're going to do is the converse of this statement that we just wrote. So it's going to say, if a rectangle has an area of 300 centimeters squared, then it has side lengths of 12 centimeters and 25 centimeters. Running out of space. Okay, now we have to ask ourselves, is this true? If a rectangle has an area of 300 centimeters squared, then it has side lengths of 12 and 25 centimeters. This one is not true. This is false. So because one of these is false, we know the whole statement is false now. But now we have to come up with a counterexample. A counterexample is going to disprove the biconditional, basically. So we need to ask ourselves, are there possible side lengths for a rectangle where it would still have an area of 300 centimeters squared? And yes, there are many options actually. So for our counterexample, we only need one. I'm going to say sides are 10 centimeters and 30 centimeters. So here I would still have an area of 300, but the side lengths are now different. So yeah, that's basically all you have to do for that one. We found our counterexample and we proved that it was false. Now, biconditionals work and pair very closely to what we call a definition. So as you know, a definition is just something that kind of describes a word or a concept. But what is the definition of a good definition, so to speak? Well, a good definition has a couple qualities, and it is going to be clear, precise, and can be reversed and still be true. So a good definition is once again clear, precise, and it's true when it's reversed. So let's look at some of these examples and show how the definition can be written as a biconditional. So here it says a pentagon is a 5-sided polygon. We are going to write this as a biconditional to kind of show that this is a good definition. So it's going to say a polygon is a pentagon if and only if it is 5-sided. So notice how we kind of broke this up, finding the subject, and then we described what it is based off of a certain characteristic that it needed to have. So we're going to do that again in example B. It says a right angle measures 90 degrees. So we're going to say an angle is a right angle if and only if it must meet this quality, if and only if it measures 90 degrees. Alrighty, so that's it for those examples. Now we just have to determine down here if these are going to be good definitions or not. So it says an apple is a fruit that contains seeds. And we're asking ourselves, is it clear? Is it precise? And can it be reversed and still be true? So this is not precise enough. So we're going to say no, not precise enough. Because all fruits have seeds. So to figure out what an apple is, we're going to need a little bit more information in this to have a strong definition. The next one is a triangle is a polygon with exactly 3 sides. This one is a good definition. So we're going to say yes. And why is it a good definition? Once again, because it's clear and it's precise. And notice it can be used forwards and backwards. So a polygon with exactly 3 sides is a triangle. A polygon is a triangle if it has exactly 3 sides. So it works both forwards and backwards, and that's why this is a good definition. So that's it for our notes in biconditionals. We'll be practicing with these in class tomorrow, and I look forward to seeing you then.